Hello and welcome back to another Prismatica Dev video. Today we're going to be talking about RVTs, also known as Runtime Virtual Textures. Not to be confused with RTs, which are render targets, or VTs, which are virtual textures. This is R Runtime V Virtual T texture. So, what is a runtime virtual texture? Well, a runtime virtual texture is essentially one big volume. So if we look up runtime virtual texture volume, we're going to scale this up to like 10,000, why not? And anything in this volume is going to be interacting with the runtime virtual texture if it is assigned to do so. So if we just chuck it down here, we're going to make a new RVT by going into our content browser, right-clicking, we're going to go to texture, and we're going to hit runtime virtual texture. I'm going to call this RVT video testo. And in our volume, we need to set our RVT video testo as the RVT that is assigned to this volume. This will essentially create, at runtime, funnily enough, a texture that is this big in this exact location. And if we go into our RVT settings, you can see that we can choose how many tiles, so how many tiles in width it is, and then size of each virtual texture tile. This means the resolution of each tile. So if you're finding that everything looks a bit blurry, just pump both of these up and you're good to go. Now, one other thing to keep in mind with these RVTs is that they kind of come with a few like preset configurations. So by default, it will be base color, normal, roughness, and specular. However, you can, if you want to save memory, just have base color, normal, roughness, or just base color. Or if you need more accurate color, you can use the YCOCG. It's like a way that RGB is packed into multiple channels just so it like compresses in a way that the colors, you get less banding, it looks better, but a bit more memory. And then there is the world height setting, which essentially stores one channel, but as I think 32-bit precision or maybe 16-bit precision. I'm really not sure, but it's precise. So we are just going to go YCOCG, base color, normal, roughness, specular, mask, and we're going to hit save. So if we grab a plane, this is how I like to debug my RVTs. We grab a plane and we make a new material. This is called debug RVT testo. We're going to chuck that on the plane. And in the material, we will grab a runtime virtual texture sample. Now, this is going to be sampling a runtime virtual texture. We click this, we find the one that we made before, which is RVT video testo. This will usually correct itself based on the sample that you give it. And it will pack page table, adaptive page table. This is just if you've got really big worlds, then there's a setting in here, which is also in the runtime virtual texture, which is right here, enable adaptive page table. That's if you've got like extremely big worlds and it needs to kind of rebase itself. We're just going to leave that off for now. And what we will do is we'll just get the base color and we will put that in the base color and we will hit save. So now you can see we have this black plane and it's super boring. So next up, we'll grab another object and we're going to give it a different material. So this is called RVT writer testo. We're going to chuck that onto this sphere. And in this one, we're going to grab a runtime virtual texture output. And that means that when the RVT goes to take a capture of everything that needs to appear on the RVT, it will be using this shader instead of this one. So you have one material graph, but it will compile a separate shader that gets used by the RVT. So if I just say, oh, I want to put in the color red to the RVT, but I want the sphere to be blue, or to use a texture, or to have some animated whoop-de-doo, it will essentially compile 2 separate shaders for that material. So you can see we have our blue sphere, but it isn't drawing a red circle to our RVT. That is because each primitive that needs to draw to the RVT needs to be assigned. So if we go to Runtime, Draw in Virtual Textures, we go Add Element, and we're going to find our RT Video Tester. Wow, we have a yellow circle being drawn from our blue circle. Okay, so what can we actually do with a runtime virtual texture, and what is the benefit of using a runtime virtual texture? Well, it's kind of in the name. So this is a texture that can update at runtime. For example, let's say like you had a bunch of buildings and you wanted those buildings to like hide the grass underneath them so that it didn't pop up through the floorboards. That would be something you can do with an RVT, because in the Unreal Engine grass implementation, these don't have any logic attached to them, the landscape grass, because they're spawned at runtime and they only exist on the GPU. That's why you can't change the parameters and you can't get collision information or delete grass instances at runtime. There's a pre-computed grass map and it will just spawn it, you know, as you go around based on that. So one way around that is to use RVTs to essentially tell it where to disable grass. So an example of that would be if I had a grass mesh. So here we have some really dodgy grass. Let's say you've got like crafting and building in your game and you plop down a floor ready to, you know, make your house. And there's all this grass and it's like, oh, why is there grass coming through the floorboards? It's absolutely terrible. So what we could do is in our grass, here's one I prepared earlier. It's essentially just, you can just look at this if you want. It will essentially just squish all of the verts down to the pivot point in, you know, the Z dimension. But we can essentially say runtime virtual texture sample. Let's just get the base color. Mask RG. We're just going to mask R. We're going to put that into the squish mask, and then that will go into the world position offset. And we need to assign the correct thing to sample from. And now you can see wherever this red is, the grass gets squished down. So we just look at it while it's up here. Boom, grass disappears. And we haven't actually affected any logic. We haven't had to go into, like, you know, the back end of the whole fucking shebang-a-bang. Now, you could apply a gradient by using, like, dummy textures or, like, dummy objects. So let's say that this is the floor of the house. What we could do is, along with our floor, we could spawn a dummy object that draws to the RVT, but it doesn't appear in the main pass. So if we go to our settings, there is a runtime. No, there is a virtual texture, and it says draw in main pass. You can switch this to never. So it will never draw in our camera, but it will always draw to the RVT. Obviously, we can see it when we're selecting it, but if we press G to go into game preview, then it will disappear. What we could do is spawn in something a little bit bigger than the floor. We could then say to the output, we could do a bit of math. We could just get our linear gradient in XY. We could apply sine with a period of 2 to each of them. And then we could max them together or min them. Yeah, choose the lesser value. So we could do that. Chuck that into the base color. We should be left with like a square looking gradient of some sort. Yeah, it's you know, it's not terrible. So let's just put that into the base color, into all, you know, the RGB and A channels. And we'll have to use like the regular cube, because this cube is UV'd very funkily. Or we could use a plane. Plane is probably cheaper. And now you can see the grass has a gradual fall off where this is being drawn, which is super cool. Now, one thing that you might notice if you had multiple of these planes, they would be kind of overlapping really funkily. You get like this weird edging going on. There's one for you zoomers out there. The way we can alleviate that is we can just draw just a flat color to the RVT, but then we can use this into the opacity, and that will actually like additively, you know, add them together with like actual opacity over top of one another. There we go. Very cool. So you might be thinking, okay, well, like this is cool. Like we can like trample the grass down. Why don't we do like a footprint system like this? And to that, I say, stop right there, criminal scum, because runtime virtual textures, despite what some people may use them for, RVTs are not supposed to be constantly updated. And there's a few reasons why. So the first is that RVTs are not additive. For example, if you were using render targets to, you know, do some like footprints, kind of like my Prismatiscape plugin, all it's doing is we have a texture and we add a shape to it. Whereas with runtime virtual textures, when you move something, it's impossible to create a trail of that thing unless you keep spawning more and more of it. The first problem is that you're constantly spawning new primitives, which can just balloon out of control and, you know, cause performance issues. The second thing, and kind of the main thing, is that anytime any of the RVT pages get updated, it has to redraw everything to that page. So if I move this slightly to the left, it has to redraw everything that is drawing to, you know, this RVT. Which, if you're doing like complex landscape materials and offloading that to an RVT, plus you're doing some, you know, grass culling, or you might be using RVTs to render flow maps, so your rivers can all blend together and speed up and slow down and whatnot. If anything gets added or moved around the RVT, all of that stuff has to get updated. And that can cause hitching. It can cause, you know, just general performance issues. It can cause memory overload and all that kind of bad stuff. So the rule of thumb is that RVTs are there to essentially trade performance for memory. It's like you're offloading performance stuff into memory because you're doing this one big operation. You know, we've drawn this texture, heavy operation, but then it just exists in memory as a texture and gets sampled as a texture in other materials, whether that's for wheel position offset or you're just trying to inherit color and all that kind of stuff. The benefit of RVTs over render targets in that case is that you can just delete things and, you know, you don't have to like subtract the exact amount from that same location and whatnot like you would with a render target. So what actually causes an RVT tile to update and refresh itself? One of the main things is just if something moves. So if something moves, then bam, that whole tile that thing moved in has to completely refresh itself. So if you had something like moving over multiple tiles and stuff, it kind of cause a bit of chaos. If we go to StatGPU, you can see virtual texture update is currently at 0.01 millisecond. That's just its kind of like idle performance cost, which is just, I guess, running the checker, you know, has anything moved, you know, undirty everything and blah, blah, blah. If I start moving this around, you can see that virtual texture appears. Where'd it go? Okay, it's gone now. But virtual texture update also like jumped up a bit. And keep in mind that this is extreme. Yeah, you can see virtual texture 0.04 milliseconds. And that's because I'm updating like heaps of different tiles constantly. And then when I stop, you can see that it just goes back down to 0 because it's finished doing everything. It's rendered its textures and now it's good to go. So this is why doing footprints and moving things on an RVT can be a little bit of a hog, as well as like if you're doing trails with it, you know, it has to redraw all of these every time. So it does actually scale exponentially. It gets more and more expensive as you add more things to it. But for something like, you know, plopping down a house and you want to get rid of grass around it, or for something like the landscape where your landscape material is really heavy, and so what you might want to do is just get all of that blending and all of that crazy texture sampling and whatever, you can just chuck that into an RVT, and then it can then sample that RVT as though it's just a texture. Another thing that causes RVTs to update is when a parameter changes in the material. So, for example, if I just had like, I don't know, just add this tiny parameter thing to, I don't know, the base color that we're sending through. So if we change a parameter, it will force the RVT to update. You can see a little bit of like weird flickering here as I do that. That's just it, you know, doing its mipping and then rendering the highest quality one and whatnot. So parameter changes will force an update. However, collection parameter, you know, global material parameter collection parameters, they won't cause an update. And this is where a lot of people run into some issues that they think is a bug, but it's technically not. So if I had a, I don't know, wind intensity hooked up into here, and that was causing this to, you know, change color, you can see when the shader compiled, it's drawn it, you know, to be white. But if I actually go to my weather parameters and change my wind value to be 0, you can see that this doesn't change. Or maybe I'll do it to 0.3, just as an example. This hasn't changed, but then if I recompile this shader, I'd need to move something for it to do that. Recompile the shader, then it will apply that collection parameter doodad. Some people will use material parameter collections to do things like change the color of their grass, you know, through seasons in their game. You know, if their grass meshes are inheriting their color from the landscape underneath, the grass won't receive that update, if that makes sense. So you can run into problems, which we might be able to see here, if the wind intensity, let's just put it back up to 1, and then we change... Where are those planes gone? Fuck my life. Then if we move this, then you can see that only this tile, since this tile has updated, it's now using the new wind intensity parameter. So if I put this back down to like 0.2 and, you know, move this around, it'll like update that one and then it will update this one. So it's just a big nightmare. And then when you move back here, it might update some of them. You can also get kind of glitches, which I think you can see here, where this resolution, this MIP level, is one value, but as we zoom out, you can then see a different value in a different MIP level, and then it disappears again. So you get this weird, like, phasing and shifting and stuff, which is not very good. So, there are also some other things to avoid when using RVTs, things that just don't work. And that is pretty much any kind of stateless material logic, such as let's say you've got like a panner, and we put the panner into our texture, and we give this panner some speed so that it will actually pan. You can see that up here, our panner is panning, but when this is getting printed to the RVT, it's completely stationary. And that is because, well, there are kind of two reasons why. The first reason is that the RVT printing shader will always use time 0. So a panner works by getting the current time, multiplying it by the speed, and then adding that to the UV coordinates of, you know, the image. And so when it's printed to the RVT, it's just time 0. So 0 times whatever the speed is always 0, so it will add 0 offset to the image. The other reason is that the panner, let's say you were getting time from, you know, a material parameter collection or something, it wouldn't be telling the RVT to refresh itself. And obviously we wouldn't want our RVT refreshing itself every frame because that gets extremely expensive very quickly. So a more applicable example is, let's say you were doing a common technique where you sample 2 images. One of them is, you know, the close texture. So this one is going to be our close texture where we want it to tile 10 times. And up here, we want this one to tile maybe only twice. And then we want to do a camera distance, or what's it called? Distance blend. So we can do a distance blend, which is the pixel depth or the distance from the camera. Let's just say the start offset is, I don't know, 500 units away. And then we want it to blend over 2000 units. And this is the alpha, so we're going to put that into a lerp. And lerp between, hopefully it starts at 0, ends at 1. We'll put that into the base color. You can see that up close, it is, you know, tiling a lot. But then as we move away, you know, to kind of get rid of the tiling, we want it to tile less. We want to have a kind of different version for the far away, you know, texture. But you can see the RVT is just really confused. So what I was initially thinking is that it was going to be like our material parameter collection, you know, with our wind value, where we moved it up, nothing happened, but then we moved this thing, and, you know, then it would update those tiles with the new value, but the other ones wouldn't have updated to that value. But what it seems like instead is that when you use distance in an RVT calculation, it actually does like the distance from the, I guess, the scene capture that would take the photo of the tile. So you can see as I move this up and down, the distance changes. So that's kind of funny. I guess it also gives you a bit of insight into how the RVTs are actually, you know, rendered. That being, you know, with a scene capture and literally just setting up a scene with the RVT assigned object in it, swapping out their shader for the, you know, the compiled RVT output, taking a photo, and then that's, you know, the new texture. So again, distance-based effects will not work with RVTs. Lastly, of the things that will not work with RVTs is parallax effects. So in this example, I'm going to use a kind of like a brick path texture. Our height is stored in the A channel. We're then going to offset the UVs of a second sample using that height value. Then we're going to unpack the normals, which is, again, just something that I have to do in my session. Put that into the normals, and let's just do like a 3 lerp color mask, because I have a 3-colored color mask in here. So we're just going to put in some colors. So we can see here there is the bump offset effect. You know, there's a kind of three-dimensionality to the texture. You can kind of see, you know, a bit of fake parallax going on here. So now you can really see, you know, we've even got like some distortion because I'm obviously pushing the effect a little bit too far. So now if we look at, you know, the version down here, there is no parallax effect. Now the RVT obviously is still going to try and, you know, compute the parallax effect and whatnot. But again, because it is just a scene capture taken from above in an orthographic view, there is no parallax to be had because there's no, you know, camera perspective or anything. So parallax effects just will not work in this case. One thing that you could do is you could put the height map of, you know, your entire landscape or whatever you're working with, and you could put that into one of the other channels. So if we got all of our height values from, you know, our landscape, and let's just put it into the roughness channel, and then in our dude down here where we're actually sampling the RVT, what we could do in this example, we are getting the world position because that's what our RVTs use, you know, to kind of determine where they are. We're using that as the UVs. So the XY is the coordinate. We then get the roughness from our first, you know, virtual texture sample. We put that into the height value. And then, you know, we would usually just put the XY into the world position. However, it expects a Z value. So we're just going to get the original Z from the world position and, you know, append that to the XY. And then the height ratio input needs to be very high because we're working, instead of in UV space, so from 0 to 1 for an entire texture, we are, you know, we're distorting the world position, which is like 1 centimeter or 1 unit per centimeter. So you can see now, if I pump this up to maybe 50, which I think is like the original default equivalent, sort of. Okay, yeah, you can see that we have the effect. It's very exaggerated. You know, we've got like some distortion going on here. But you can see that, yes, the bump offset effect is working, and it's working correctly. So you can sort of get around, you know, parallax effect by including the height map in your RVT, you know, in one of the channels somewhere. Basically, anytime another material needs to know something about any other material or any other object, RVTs are one of the most performant ways to actually achieve that. One of the most common ways to implement RVTs is to blend things in to the landscape. So let's say this is our landscape. Inside here, we might have a bunch of like really complex logic going on. What we can do is, instead of plugging all this complex logic straight into the base color output, which gets drawn in the main pass, what we could do is offload it to the base color of an RVT and then sample that RVT into the base pass, or the main pass, sorry. Now you'll see that this is black, but that's because I haven't assigned our landscape, in this case, to our runtime virtual texture, RVT video, testo, bam. And now you can see that it is outputting to this RVT. You can see just in the tiny little thumbnail down here. And if we actually look at the shader complexity, then you can see that it's at least different in this case. It will probably be slightly darker than if it wasn't there. So if we were just going directly into the base color, but that's because RVTs have a slightly more expensive overhead than a regular texture because it has to unpack, you know, which tiles and all that kind of stuff. But shader complexity won't change as you add more complex things and more layers to your landscape. But you can imagine that if I was doing a bunch of landscape stuff that was putting it like into the red, you know, really complex stuff, then this would still end up being cheaper. One thing to keep in mind is that if the RVT is really low resolution, then the result will be, well, you guessed it, low resolution. Who would have guessed? So if you're doing stuff like just data, you know, for example, my water data stuff doesn't need to be very high resolution, then I can kind of back off on the settings. But if you're doing something, you know, for example, your landscape, then you probably want to just adjust these until it's so sharp that you can't really tell that there's a difference in fidelity. So we're offloading our base color to our RVT. The other thing we could do is, so you might have a separate normal texture, but I just pack them all into here. I'm going to put that into the normals. And then the other thing that we might do is get the world position in the Z axis and put that into the world height. We'll want to get the normals out of here, put them into there. And now you can see that we have normals. Wow, look at those. Look at those normals. So I'm going to make just a debug plane up here, which is going to just have another material, which we're going to use to debug some stuff. Runtime virtual texture sample. I'm going to grab the normals and put them into the base color. So now you can see that these are the normals that are being drawn to the RVT, essentially. But you'll notice that if I rotate this, the normals don't change. And that can be a bit of a problem, because if we actually look at the normal buffer, you can see that the normals are, you know, turning purple towards red, and, you know, if we go that way, they turn green, and all that kind of stuff. The things that you put into the normals of the RVT, you need to actually write it in world space. So if we go back to here, before we go into the normals, we just want to transform, and we want to transform from tangent to world space. Put that into the normals, and then if we hit OK, then you can see if we start rotating this, it will actually change the normals, you know, to reflect how they're actually supposed to be. However, you will notice that now the ones that we're sampling on our landscape are incorrect. It'll essentially be like doubling it up. What we do need to do is, on the other end, we need to transform it back from world space to tangent space. So now that we're turning this back into world space, you can see that it is good now. So if we got this mesh, and we actually just changed this to be like, do I have like a mountain mesh? That's quite large. Holy shite balls. So you can see now, because we're transforming to world space, the actual like mesh normals get written into here as well. And that can be extremely beneficial for the next thing that we're going to talk about. Okay, so here we have a cliff, and it is sitting on our landscape. You can see there's like a really harsh edge, you know? And like if I was trying to use this as like some texturizing, like I just wanted it like just coming out of the ground like this, you know, like making the ground all rocky. You can see that these like sharp edges, I just don't vibe with them. Do you know what I'm saying? I just don't vibe with them. They fail the vibe check. So what we would want to do if we're using RVTs in general is, firstly, we would want to create another RVT volume, which will sit over the top of this one. So this one here is for the color and all that other stuff. Let's just copy, paste, and we're going to make a new runtime virtual texture. This one's called RVT Video Testo Land Height. And we're going to go into this, and we're going to go to its compression settings, and it's going to be world height. We can probably just lower these settings a bit. It doesn't have to be as high res. Let's go to our landscape, and we're going to tell it that it is allowed to draw to the RVT Video Testo and Height, land height. really struggling. So now the landscape is subscribed to it. We need to assign it to its volume. So you can see we've got these two overlapped ones. We need to actually assign it to this volume. You can see now it's having things drawn to it. You can see it's like grayscale, which is like a height map. And now in our cliff, we can begin to work some magic. So let's go into our cliff. We're going to get runtime virtual texture sample. We're going to get the world height, which is a scalar value. We're going to subtract the world position of this material. And then we're going to divide it by a number. This is like our blend, the blend distance. Sorry. If we go into unlit mode, you can now... Oh, you know what I'm doing wrong? I, again, for like literally the 5th time this video, forgot to select the thing that we actually want to sample in the material. Happens every time. Okay, now, eureka. Now you can see that we have black up here, white down here with a gradient of 50 units. However, it's the wrong way around. So let's just flip these bad boys. It's always trial and error when I do this kind of shit. I can never remember what it is. So now we have black here, we have white up there, and it's probably easier if the white is on the bottom value. So we're going to saturate this, and we're going to 1-. So now you can see we have this beautiful mask of white to black. So what can we actually use this for? Well, glad that you asked. We can use this in a lerp, and we're going to lerp between our other runtime virtual texture, which is our color. So color is white. The original color is going to be our black value. Chuck that into the base color. And then for the normals, we are going to get the normals out of here, and we have to convert it from world to tangent space. And that's going to go into number 1. This goes into blah, blah. Sorry, A and B. My brain's fried. And now you can see that our mesh blends into the landscape quite nicely. If you look over here, it's a bit more, obvious. But and you can see there's no discernible line, and that is because the normals are blending as well. So if we actually look at this, we go to the normal buffer. You can see that on the edge of this cliff, like where it meets the landscape, it still has upward facing normals, which is physically incorrect, but it just makes it blend smoothly, and you don't get like weird shading lines. Now, this is why it's really handy to store the normals in world space, because if this mountain was like, oh fuck. If this mountain was a bit steeper, then the normals, they're going to be pointing in the right direction. It's not just going to be the tangent space normals. So if we had this cliff and it was like, we were like blending it in and like doing all that kind of stuff, then, it would be pretty seamless. You can see when I move it around, you can't really tell where it starts and where it ends. Now, obviously you could use like some noise to like noise this up a bit so it isn't just like a smooth transition. If you want to learn how to do that, look at my height lerp video. You can also just adjust, the amount of blend. So you could make this less, or you could make it more, or you could, make it like more exponential so that it's more like curved. It's like stronger here, but then it like tapers. I'd want to do that after this, wouldn't I? Yeah. To push it down more towards the landscape height, which might give you better results. It really depends on what you're actually using it for. Super, super handy technique. This is like one of those must-have techniques that you need to know. One other thing worth mentioning is if you are doing blending, One way to alleviate the cost of RVT sampling is to actually use a vertex interpolator. So if we got our blend mask and we then put a vertex interpolator, you know, at the end of our blend mask, you will see that for, you know, kind of more high poly meshes, there won't really be much difference in the mask. And, you know, if there's no difference in the mask, then it will pretty much look the exact same as before. However, for some meshes that aren't as high poly, you can see that the mask can kind of get a bit funky because it's sampling it per vertex and there just aren't enough verts here to create, you know, a smooth gradient. However, what we could do instead is just put our vertex interpolator right here. So it will be getting the, you know, the world height per vertex, but then it will be doing the actual blend at the pixel stage. And so this will still offload a lot of pixel instructions. So here we're at 377, and then here we're at 288, and with still a perfectly smooth gradient that doesn't really look any different to the, you know, the pixel stage version of it. Now we could take this one step further and actually, you know, vertex interpolate the base color from the RVT and the normals from the RVT if we so wished. And that would just offload pretty much all of our runtime virtual texture sampling to the vertex shader, which again saves a ton of performance. But then all of the color from, you know, the RVT and the normals from the RVT are going to look like blurry. You can see here it's just blurry, and this is because rather than being per pixel sample the RVT, it is per vertex sample the RVT. And so that's why it ends up being blurry and looking a bit funkalicious. But if your landscape is predominantly just like flat colors or smooth colors and, you know, not very much normal detail going on, then vertex interpolating can be a very good performance saver to offset a lot of the cost of using an RVT. And obviously you could choose to just do the color through the vertex interpolator, or just the normals, or just the height, or any combination. And so you can use vertex interpolator creatively as well. So for example, if you were using like full detail landscape textures and whatnot, but you wanted some foliage to kind of be a bit blurrier, like, you know, for the blending to be a little bit blurrier, you could utilize this creatively, but it's also just a nice performance gainer. And if you do want to learn more about vertex interpolator and, you know, the performance benefits of it, you can check out my vertex interpolator video. So one thing I've come across a lot while working on my landscape material is that I want some things to draw to the RVT, but I don't want other things to draw to the RVT within the same material. So to control the flow of what does and doesn't get drawn to the RVT, there is actually a node called Runtime Virtual Texture Replace. Now, this is a really dumb name, and so this might have like gone under everyone's radar. This should really be called Runtime Virtual Texture Switch, which would be, you know, the same as the feature switch and the nanite switch and the scalability switch. The quality switch, which is, you know, out of order. It goes low, then high, then medium. Can someone just like fucking fix this? Like, come on. I had to make my own one that just... anyway. So, this Runtime Virtual Texture Switch node can be really handy if you are doing things like, you know, landscape and foliage interaction, if you're doing procedural puddles that, like, you know, when it rains, you have like an animated kind of thing and like puddles form on the landscape. You don't want those puddles going into the virtual texture output because you'll get that weird shimmering where like it will update in a particular state and all the MIPs will be you know, out of order with one another, and it's just a complete nightmare. One thing that would be really nice, honestly, would be a runtime virtual texture switch that was like, kind of like the new switch node, where you can like add extra parameters and stuff. It'd be really nice if you could have like a default and then add RVTs that it gets drawn to, and then put it into here so that like different RVTs could grab or could, you know, compile different shaders rather than having to like duplicate the mesh and do like a dummy RVT drawer. So you could just do like an all-in-one to multiple different RVTs. But again, that's just a wish. That's just on my million entries long wish list of Unreal Engine features that are never going to be done because Nanite and Lumen and other, you know, shiny things. Now, one thing to note, when you're using like landscape height and whatnot, you may potentially, possibly, figuratively, hypothetically want multiple landscape height RVTs. So in my case, I have one for the landscape, as in like the actual landscape, you know, mesh thing, which is used for blending things into the landscape, funnily enough. But then I have another one, which is called the interaction height, which the landscape does draw to, but then other things draw on top of it. So for example, this cliff would be drawing to the interaction height, and the landscape would be drawing to the landscape height and the interaction height RVT. Now, the reason for that is that you might be using a plugin such as Prismatiscape that needs RVT height data to actually like do its interactions and stuff. And you can see that even though my landscape is down here, my interaction height is on top of, you know, some other objects. And so this is like what the player can walk on and what would be expected to be interactive. This also applies if you're doing things like using WPO stickers, which I cover in a video, which I'll show some footage of here, but you can just look up WPO stickers in Unreal, where essentially you want things to adhere to the ground, and that is like, you know, what the player perceives as the ground, not just the landscape that, you know, props are put on top of. You want it to interact with, you know, the rocks and logs and all that kind of stuff that would be on top of the landscape. So that's why it can be handy to have multiple height channels. RVTs are quite poggers, as the kids say. What am I saying? I'm basically a kid, you know. I'm basically still a kid. I'm only 30. Other uses of RVTs are things like having things inherit the color from underneath them, which I have, I think it was my very first YouTube video about coloring stylized grass. That uses an RVT to, you know, color the grass based on the landscape. All right, and the last little example that we're going to go over is drawing like roads and other kind of like stamps to an RVT. So this is provided that your landscape is sampling an RVT, or you could use like a dedicated RVT to just, you know, roads and paths and like kind of like decals, but they're cheaper. So how we'd want to go about this is, in this case, we're just going to get a runtime virtual texture output. We're just going to get a texture sample. We're going to get a brick. We're going to unpack the normals because that's something that I have to do in my project specifically. We are going to use the height. So I've got a height map stored in here. Oops, sorry, in here. We're going to use the height and an radial gradient exponential. We're just going to put this straight into the normals. And we're also just going to, let's just put a color in. Why not? You know, we'll put in multiple colors. Why not? We'll use the color mask that I've got in here. We'll do lerp, and we'll lerp between two different stone colors, I guess. I don't fucking know how do roads work. That's going to go into the base color. Normals go into the normals. And then we're going to get the texture, subtract 1, this multiplied by 2, add them together, bam, bam, apply some contrast. That's going to go into our opacity. And now, if we go and tell this plane to draw to runtime virtual texture, we're going to draw this to this one. And you can see that if I make this bigger, really shitty example on the colors there. I'm going to change the colors of these just so they're more visible. It's going to be a green path. Green and blue. Okay, there you go. And now you can see we have this, this kind of pathway stamped onto our schmoobly doobly. If you do want a more in-depth video about drawing roads and other details to your landscapes and your levels and stuff, I do have 2 videos called RVT Roads and Paths, and another one called like Circular Town Center or something, and they both use RVT stamps, and I go into a little bit more depth on how you can actually make it look good. Now, one thing that you will run into, and this is kind of the reason that I'm going over this explanation, is sometimes you'll want some things to draw over the top of other things. So for example, if you're drawing roads and stuff, you always want them to be drawn after the landscape. And the way that we do that is extremely unintuitive. It's by using the translucency sort priority. Why there isn't a runtime virtual texture sort priority, I don't fucking know. Just Unreal things. So if I put the landscape at number 10, it's going to be drawn 10th priority. These are everything set to 0 by default. So if I then set this to 7, it's not going to draw. But if I set it to 11, then it will draw. If I set it to 10, then it's kind of just chance. It might know which was placed, in the editor first, but sometimes you don't want to take your chances. One of the things I'll do first is set my landscape to -1, just so everything draws on top of it. And then what I'll do, if I'm using like some RVTs for really niche, weird things, for example, drawing the river velocity to a color RVT, because velocities and directions have positive and negative, we have to do, left and right and up and down. What I need is for the default color to be 0.5, and you can't just do that in a runtime virtual texture for some reason. Again, another thing that they should bloody add to friggin' RVTs is a default, default color or a default value. What I will do is just get a plane and make it really fucking big and put it really, wherever it needs to go, or just like, disable it in the main pass. And then I'll have it set to -1 billion, just a really low negative number, so that it's always drawn first. And that will essentially set up like a canvas for me to then draw all of these velocities to. So that would also come in handy if you wanted to do something like an RVT, for like foliage lushness, for example. You might want the RVT to start at 0.5, and then as it moves down to 0, things become, dry and dead and barren. And as it moves up to 1, they become like lush and green and all that kind of stuff. So, one other thing that I just want to add to this video is that RVTs can be sampled in Niagara particle systems. Now, why might we want to do that? Well, as an example, let's just go and create a new Niagara emitter, and we'll just get a fountain's probably a good way to start. So we have this fountain, and it is shooting out some particles. Maybe we want the color of these particles, imagine this is like an impact effect. Maybe they're like little dust puffs, and you've got some, different colored dirt and sand around the place. what we can do is go into the Niagara system, and we want to say on particle spawn, we're going to do a new scratch module. We're going to say map get runtime virtual texture sample. We're going to sample RVT. Well, because this is happening on particle spawn, in the particle spawn stage, we can just get the particle position. So this will essentially just be the initial position of the particle. Sample the RVT at that position, and then we could do map set color. How do you spell color in Thingo? Core parameters particle color, and we'll get our base color. That can just convert to linear color. Now, okay, we're getting an error. Sample RVT does not work on CPU sims. So what we would have to do is go to our, emitter properties. Gonna go GPU compute sim and do that. And in this scratch module, we have to click on it and we have to actually say, use this, RVT video testo, and go to here. It's a pretty shit example. I might even just get a new material to add to these that isn't translucent. And there we go. Okay. So it's a lot easier to see now. So you can see as we grab this and we move it around, the particle color changes based on, what position the particle is coming from. So if we start kicking up dirt over here, then we're kicking up little dirt particles, and then we're kicking up stone particles, and in this very little spot here, they're like little grass particles. If we increased the shape location to be like a radius of, 100, so these particles are just going to come from anywhere. So you can see it's a mixture of, the particles that are coming from this location are going to be gray, the particles coming from here are going to be brown, and the green ones are going to come out of the grass. So if you had some, grass color variation, using lerps and textures and stuff, you would be able to say, there's, more yellow grass coming up from this point when a character falls there versus green over here. And if the grass was kind of, a bit more brown because it's near dirt, the particles would match that color. So that's something handy to keep in mind about RVTs. Another thing you could do, and I won't do it here, it's a bit out of scope for this video, but for GPU particles, you could also use RVT height map, so RVT world height. You could essentially use that as like a form of collision instead of, using distance fields. So for example, you might have some water and you wouldn't want that water to be emitting distance fields because the water, usually you'll be using distance fields for the water, to react to the kind of shorelines and stuff. So the water doesn't have any distance fields. You have a bunch of GPU particles, so you can't just, collide with the water object for the collisions. You could essentially use an RVT height map as a collision for, water particles or little things floating on the water. You could even write it as almost like a buoyancy simulation. So you could say, as it gets further under the water, it will, emit an upward force on the particles. Or you could just use it as if it goes below this point, snap it up to, the water height. The other thing you could do is if, like me, you're drawing your water velocity to an RVT, you could actually have particles react to, the velocity of the water, which would be really cool because then, you've got a bunch of particles, they're floating on the water, and then they're also moving down the river. Now, obviously, you would want to do this for like very non-gameplay related particles. So if you had like an object floating down the river, you'd want to be doing that on the CPU side of things with your buoyancy and river system, however that's set up. But for just massive amounts of little particles, you could easily do that in here. And that kind of segues into another little discussion about optimization and kind of some of the shortcomings of the current RVT implementation. So there is nothing preventing you from just making heaps and heaps of different, RVT volumes and RVT textures. And in some cases, it can be more performant to do so, especially with things that are, updating frequently. So, if you're removing patches of grass, let's say you're doing like a farming sim game and you need to, change the soil when you plant something and you need to remove grass and other, micro foliage and whatnot. In that case, you are updating fairly frequently. And so you might just want to be generating a mask in a completely separate RVT. Maybe that's called the soil RVT. And the benefit of that is that every time you then plant, a new plant or place a new building or whatever, bam, 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 it doesn't have to go through and render your, potentially very complex landscape material. And obviously then the capture cost of the RVT is going to be less expensive, so you'll get less hitching overall. Also, if you had heaps of different objects, within a tile that were printing to the landscape RVT, those also wouldn't need to be rendered in the scene capture every single time you placed a new object down. So in that case, you would, like in our earlier example with hiding the grass, you would just have an RVT that is just for the masking, and then in your landscape material, you would pull out whatever the mask was, and then, blend between grass and dirt and that kind of thing. However, one of the drawbacks of using multiple different, niche dedicated RVTs is that currently, and it's a little bit, it's kind of annoying, when we are sampling a runtime virtual texture, obviously we're using this runtime virtual texture sample node. So already you can tell that this is it's a special operation. It's not just like a regular texture sample. And essentially what this is doing is it's kind of like unpacking and sorting and piecing together this kind of virtual texture, array of textures that we have set up. When we're using, the sort of default setting that has, all these ones, specular roughness, normal, mask, etc., it's actually kind of stored in three textures within the texture, if that makes sense. So if we have base color, our instruction count is 282. Obviously, instruction count isn't really a metric of anything, but we can compare it to itself. So if we get base color and we add specular to that, and then put that into our base color, you can see that our instruction count increases slightly, up to 293. If we then add roughness, you can see we only gain one extra instruction. And that's because, specular roughness are packed into the one, the R and G channel of, the thingo. I think the same goes for the mask channel. If we're using the YCOCG BBBBB thingo. So it's jumped up 4 extra instructions. Cool. So you can see that there is sort of, depending on the, the grouping of textures that you are using, there is an increased cost. However, the biggest cost is sort of the upfront, piecing together of this whole shebang-a-bang. So without the RVT at all, 137. With the RVT, even just using one thing from it, we go up to 282. Even if we're just using, one of the singular channels. If we just had a copy of this node, and we had, the specular here and the base color, and we added them together, This isn't really going to make a big difference. You know, you can see that we're just at our usual, you know, 293. That would be the exact same if I'd just, you know, done it from here. That's just because the shader compiler is very smart. It will remove, you know, duplicated nodes and, you know, store it as a local variable, that kind of thing. However, if we just had a different RVT and we added its specular into here, you can see that our instruction count jumps up exponentially. And this is kind of one of the annoying things that I don't really like about the current RVT implementation is that, and again, this is just my speculation, but I speculate that a lot of the upfront cost comes from, you know, getting the runtime virtual texture bounds and, you know, doing all the tile sorting and all that kind of shit. And then once all that's sort of in position, it just samples it, you know, sampling the textures. But you can see that these two volumes have the exact same location and the exact same scale. And ideally, we could just tell them to even have the same tile length. So we'll do, you know, 5 here, and in here we'll say 5. So again, all of the calculations for unpacking and packing these RVTs are identical, but even though they are identical, it still has to run, you know, that heavy operation twice. And so if you did have a lot of dedicated RVTs for, you know, with our example before, something to hide the grass, you would need to be using multiple RVT, you know, sample nodes with different textures. Again, even if they all had the same number of tiles, same resolution, same positions and stuff, and it, you know, you would just be incurring a lot of extra shader cost. You know, 100 and something instructions per new RVT. So currently, the most performant thing to do is to just try and pack everything into the one RVT set. So that is the base color can be used for the base color. You could use the specular for your, you know, grass hiding mask. You could use your roughness for, you know, where you do and don't want puddles to form. Normals are for normals, and mask is, again, just another extra channel that you can do something with. You know, maybe this is for the height texture, for height lerping and whatnot. And, you know, if I just chain all of them together and put that into the base color, you can see that the instruction count, even though I've got, you know, 3 or 4 textures worth of stuff in here, the instruction count is less than using 3 separate RVTs. So again, just to reiterate, currently, with the current implementation of RVTs in Unreal, it's best to sort of group things into kind of broad categories. So in my case, I have, you know, anything to do with the landscape, you know, hiding grass, you know, having soil exposed when something's placed down, the color of the landscape, that's all here. But then the water stuff, the water flow direction and flow strength, the water classification, so classifying, is this a river, is it a lake, an ocean, is it a shoreline? You know, I do like a shore mask with RVTs to get shore waves so that, you know, wave towards the shore in a deterministic way. All of that goes into a water data RVT. And the reason for that is that I'm only going to need to sample one RVT in my water shader, which is the water data RVT. And I don't want to have to sample something from the landscape RVT on top of that, because it's just going to add a lot of performance ballooning. So what I would like to see in the future is just like either being able to synchronize, you know, volumes together so that when they're sampled in the shaders, they don't incur that extra overhead. And usually if you're doing something like blending something into the landscape, you'll be sampling the normals, you'll be sampling the color, but also the landscape height. And the height is, you know, it has to be a different RVT. So it would be nice if you could sync volumes together, or alternatively, just be able to have multiple virtual texture, you know, kind of inputs in here, so that you could say, okay, yeah, this volume is dealing with the color, and it's dealing with, you know, press the little plus icon, and it's dealing with the landscape height, and it's dealing with the water and the water height. Obviously, they would all need to be the same size in tiles for the calculation to be, you know, just computed once and then thingoed. But that is just, you know, something on my wish list. Maybe I'll look into engine source code to, you know, figure it out myself, but maybe in the future, the textures will be able to share, you know, the upfront cost in the shader. But that about wraps it up for this little introductory video to Runtime Virtual Textures. Sorry, it's been a bit of a long one, but there's just a lot of use cases and a lot of like technical mumbo jumbo that sort of needs to be explained with Runtime Virtual Textures. Keep in mind, there are like a million other things you can do with RVTs that I haven't really gone over in this video, but hopefully this little introduction has like given you a starting point, and you can start like juicing your own ideas around in your own head. So as always, thank you very much for watching. If you did enjoy the video, make sure that you subscribe to the channel for more. Hopefully I'll be uploading a bit more regularly. If you do want to watch any of the things I do live on stream, you can check me out on Twitch at PrismaticaDev, twitch.prismaticadev, fucking, I don't know. And if you do want to support monetarily, you can do so for as little as $1 per month through the Patreon, which is linked in the description. So thank you very much to all of the patrons. You guys are absolutely fantastic. I really appreciate it. And with that, we say goodbye. Goodbye.